But let's begin. So I'm happy to have Chris give this next talk. Thank you, Chris.
Okay, can you, is this working? Can you hear me? Okay, thank you. So I want to talk to you today about both a number of different topics. H1, dark matter, the magnetic field. Alternatively, I could have called this, oops, is this going to work? It's not working. Okay, I'll do this. Dick and Carl at play in the fields of the ISM. So unfortunately, Carl is not here yet. This was the picture I was able to get of Carl. You can see, and also Leo Blitz is the person in the front. And Carl looked a little different then, but the level of intensity, I think you can see, was still similar. Now, actually, I didn't have a photo of Dick. So I don't know, Dick has sort of looked about the same ever since I met him. Perhaps he's ageless. Okay, so let me get started then on the first part of the talk, Carl H1 and the dark matter. So I want to talk to you about some work we did recently on measuring the amount of dark matter. And the interstellar H1 is crucial in that. So let me start up here. If we want to determine the total surface density of matter within some distance, this is within 1.1 kiloparsecs of the galactic plane. People some time ago determined the total amount of matter from looking at the kinematics of stars. If you then determine the surface density of the baryons within that distance, it turns out the H1 is the most uncertain. In a recent review, Reed estimated this surface density around 12 plus or minus 4 solar masses per square parsec based on the lab data by Calberla and Dides. And this error then, as you can see, dominates the error you got for the total for the baryons. Once you know the amount of the total mass, the baryons, you subtract them and divide by the distance, and then you can get the dark matter density. So let's start. Now, I go all the way back to Carl's work in 1976, and you can then get, assuming that the H1 is optically thin, this is the amount of H1 that you find. At that point, he just was fitting a linear line and didn't attribute any physical significance to the negative sign there. Now, subsequently, he looked at that and realized that there'd been some stray radiation, so he made a correction for that and pointed out that this negative sign actually corresponded to the fact there was a hole in the local H1. And so if you can, subsequently after that, in fact, it was realized that's what we call the local bubble. And so if you just write down what is the total column density of H1 in the optically thin limit, then it's the amount that is perpendicular through the plane, then times the cosecant, but then minus this hole that you have, which he then determined by averaging over the sky. Now, of course, in fact, we know the local bubble is very far from spherical, so this is just sort of an average, but it does give an accounting of the total amount of H1. And for example, you can then compare this with the Bell Labs H1 survey. Lockman and Gaiman got an average of the total amount of H1 above 45 degrees, about 4.2 10 to 20, and this model, which I call the Heiles model, gives you 4.3 times 10 to the 20. Okay, so now we want to compare this with the lab survey, and the Heiles model, rewriting this, that if I just go ahead and get the total perpendicular column density through the plane all the way from the bottom to the top, that's 8.45 solar masses per square parsec. If I then, I cited Reed's interpretation of the Calberla and Dides result from the lab survey, 12 plus or minus 4. And then in a private communication, I had a number of communications with Calberla. He actually then looked back at his data and found that it's actually closer to around 9. solar mass per square parsec. So that's actually, again, implies there's excellent agreement between the Heiles model and the more recent data. So what about the correction for optical depth, which we've already heard about earlier this morning? So I just defined R as this ratio of the total H1 to the optically thin H1. If you look at the Canadian Galactic Plane Survey, which was in the plane of the galaxy, they found 1.32. If you look at other galaxies nearby in the local group, Brown found 1.34 plus or minus 0.05. I then looked at the data from Carl and Tom and just average over all the lines of sight less than 40 degrees. I picked that because there was really hardly any absorption above 40 degrees. And we know that the absorption is in the CNM, and there is no CNM at high latitude. In any case, you get R 1.29. So we then just went ahead and adopted a typical value of 1.3. Now, that is for all the H1. We know that the absorption is in the CNM. And so if you want to know what is the value of R for the CNM, you can show that you have to subtract off the warm neutral fraction. Then using the result from Dickey and Lachman that the warm neutral fraction is about 56%. That says that for the CNM, the total ratio here is 1.68. So then we've already heard from Yasuo this morning, and if you compare with him, as he described, he used the 353 gigahertz Planck data plus 100 micron IRAS data to infer the dust temperature. And then he used this lab survey, integrated over a very wide velocity range. And for B greater than 15 degrees, he found that this ratio R was 2, which is significantly bigger than the 1.3 that we found. And he concluded that there's a significant amount of missing gas. Now, the interesting thing is that if you go ahead and apply the Heiles model, including the optical depth correction, to his results, that is, he said how much mass there was, and I can compare how much mass you would get in the Heiles model with how much mass he gets. And in fact, you infer that this ratio is only 1.22. It's actually less than 1.3, which is what you would expect because there's not as much CNM above 15 degrees as there is over the whole sky. So the reason for this discrepancy between his analysis and our analysis is not known. As we heard in a subsequent talk, it could be that there are issues with the conversion between the optical depth of 353 microns and the H1 column. In any case, if you go ahead and extrapolate to all B, he finds a somewhat larger ratio and he attributes that to opaque H1. We would attribute that both to the fact that R is actually a little bit bigger than 1.22 and to the dark gas, whereas Isabel referred to it the dark neutral medium. Oh, and I should mention that in a paper in 1988, Carl almost discovered that because they did an analysis in which they were talking about how much CO there was in H1, and they got very close. So we then tabulated all the results, we collected all these data, and this you can have, not only do we give the midplane density, we also have estimates of the scale height from various references. And then this gives the total perpendicular column density in particles per square centimeter, or actually hydrogens per square centimeter. And then here is the solar masses per square parsec. And then this is the amount within 1.1 kiloparsecs of the plane. And the opacity corrected, anyway, the opacity corrected Heiles model, we get a total H1 of almost 11 solar masses per square parsec, total gas 13.7. And W&M to H1 is 43%. And if we compare that with McCall 92, in fact, John got almost the same value that we did. He had more H2, and did not include an opacity correction for the H1. Whereas with Reed et al. Got significantly more than that because he has this significant overestimate from the Calberla and Didius. Okay, so then we can go ahead and actually calculate the amount of dark matter. So let me remind you that the baryon budget for less than 1.1 kiloparsecs is we have 12.6 solar mass per square parsec in gas. In the stars, we've determined that from previous authors and by reanalysis and got this value. So we get a total amount of baryons here. Then we take the amount of for the total gas that I showed you earlier, and we get a dark matter density of about 0.013. Solar mass, I miswrote that. That should be per cubic parsec, excuse me. And that's consistent actually with most of the recent values, a little bit higher toward the high end, and you have to make some suitable corrections. And by comparing then with the gas density is 0.041, that corresponds to a particle density of 1.17, and the total baryon density of 0.084. So that's significantly larger than the dark matter, of course. Okay, so the conclusion for Carl is that this work, this pioneering work that did decades ago, has enabled a significantly improved estimate for the total amount of H1, and that then enables us to estimate the amount of dark matter. So, yes. Okay.
Airplane mode.
Yeah.
Up here.
Right.
I'll show you.
Yeah, tell me yes. Okay.
Just slide up. From the bottom, if you slide up.
There you go. Okay. Thank you. Okay, so now I want to talk about the work on magnetic fields that Dick and Carl did, and first discuss observations. And Dick said he'll talk more about this on Friday. And then we actually went ahead and did some simulations to compare with that, and then talk about the recent critique of their work by Tritsis et al., and talk about the work that Hua Bai Li did on the mean magnetic field. Okay, so this is a famous figure that Dick has already showed, which summarizes all the existing Zeeman data at that time. You have the line of sight magnetic field as a function of the density. And down here you have mostly H1, this is mostly OH, and up here we have CN. And the important thing to realize is that only 27 of these molecular points actually are more than 2 sigma. So most of the points are actually they hit less than 2 sigma, and traditionally had been ignored. The advance that was made in Crutcher et al. Was they used a sophisticated Bayesian analysis to go ahead and include all these data points, including the upper limits, in order to infer the 3-dimensional field. Okay, now the first important conclusion they drew from this work was that for above this break here, which is mainly molecular data, the total magnetic field varies as a power of the density, which is about 0.65, very close to 2/3. The second important point they inferred was that the distribution of, if you took the magnetic field and normalized by this density dependence, that's fairly uniformly distributed between some value f times the maximum value up to some maximum value. And that f here is very small. So basically it's a uniform distribution from very small values up to some maximum. And that implies that a significant fraction of the volume of the interstellar medium has low magnetic fields. Okay, so the first thing we did was to actually reanalyze their data, and we actually did it much simpler. Rather than looking at trying to do a more sophisticated analysis, we just went ahead and looked at the line of sight fields instead of the total fields, so that just using their data. And we did numerical experiments to show that you should just treat all these data equally and not worry about their statistical significance. This does assume that the errors are statistical, not systematic. And the first thing we did is we confirmed their result. The line of sight field also varies as the density to a power. That power we found was 0.63 plus or minus 0.07. So that's very consistent with their result. But we then can go and find something else. We can actually put in the coefficient in the proportionality. The average line of sight field is 21 times the density in units. This is hydrogen density in units of 10 to the 4th to the 0.65. And then since the total field on average is twice the line of sight field, this allows us then to determine the magnetic field in molecular clumps. And we don't have, unfortunately, I don't have an uncertainty here, but this, I think, is a remarkable result. And when I was talking to Fumitaka this morning, he has a new result with a completely new molecule, and assuming this is accurate, say within a factor of 2 or 3, he will show that it's consistent with that. Okay, but then we went ahead and did a simulation to try to see to what extent we could reproduce these results. And there are many differences between the simulation that we did and the observations, of course. So first of all, these observations were, as I mentioned, they're essentially all the data that's available on Zeeman observations. It's a completely heterogeneous data sample. And we have one numerical simulation. The observations are smoothed over a scale which depends on the resolution of the telescope and the distance. And our simulations, we just smoothed on a 0.03 parsec scale. The maximum mass in our simulations turned out, for our clumps, turned out to be about 74 solar masses, whereas in the observations, they range up to well over 1,000 solar masses. The simulations do not include non-ideal effects like bipolar diffusion, whereas, of course, the real observations include everything that Mother Nature can throw at us. So we used a high-resolution simulation using our code Orion 2, and included in the physics is just ideal MHD and self-gravity. We have periodic boundary conditions. We drive the turbulence at large scales throughout the simulation. We turn on the gravity after 2 crossing times when the turbulent density field is established, and then our resolution was 512 cubed with 2 levels of refinement, so for a maximum resolution of 2048 cubed. Dimensionless parameters, you can see we just picked round numbers, sonic Mach number of 10, alpha Mach number of 1, gravitational energy about equal to turbulent energy, so the real parameter of 1, and then that determines actually the mass to flux ratio, which you can show is related to these quantities up here, and it was 1.6. So our initial simulation was magnetically supercritical. So here's a picture after half a freefall time, and these are the mean density is almost 1,000, but because of the turbulence, half the mass is at a density above 5,300. We have about 3,000 solar masses. The mean magnetic field is 32 microgauss, and the best resolution is 500 AU. We then chose the 100 most massive cores to analyze, and all of these have a mass bigger than 1 solar mass. Also, I should mention that the size of our simulation box is 4.5 parsecs. So the density scaling agrees with observation. So Crutcher et al. Found that B total varied as density to the 0.65. We now, of course, in our simulation, we don't have to project and do a fancy analysis. We just can measure directly what the total magnetic field is. And this, we have a number of different time slices. If you average over time, we get that it's 0.7, and that's plus or minus 0.06, consistent with their result. For their 68 cores, their median of this B line of sight over n to the 0.65 was about 11.9. For us, it's 8.9. And then for the total field, it's about twice that. So there are 2 consistencies here. First of all, the median value of the total field is about twice that of the line of sight field, which is what you expect. The simulated value we have here is 3/4 of the observed value. And I want to emphasize again that we just picked all these round numbers and did one simulation, and this is remarkable agreement really for trying to simulate the real world in a very heterogeneous data set. And another thing, of course, we can do, this nice correlation here, as I mentioned, we first drove our simulation without self-gravity, and at the end of that driving, this correlation did not exist. All the points were down here. Only after self-gravity was turned on did this correlation get established. So we can establish the physical origin of that correlation. If we then compare the distribution of the line of sight field with the observed value, then we find that that's consistent with applying a KS test. And however, when we try to look at the PDF of this, we do not get a uniform distribution. Instead, we get a very good fit to a log normal distribution. So the conclusions from this simulation are that, first of all, we have excellent agreement with their observed result that the total field scales with the density to the 0.65 power. We get very agreement with the distribution of the line of sight field, the normalized, and the median values differ by only a factor of about 1.3. But we find that the distribution is log normal instead of a uniform distribution. Okay, now many of you are aware of the fact that shortly after this paper was written, Tritsis and one of the people in the plus there is Telemachus Musavias, who every time Dick writes a paper, Telemachus writes the anti-paper. So this was the anti-paper. And they claim that the observations in Crutcher et al. Are fit much better than alpha 0.5. And of course, Telemachus had said that about 40 years ago. They then, and he pointed out, of course, that had been well established way back by Mastella in 1966, that this value of 0.65 is very close to 2/3 of what you expect if you have the contraction of a spherical cloud with a weak magnetic field. But we should notice, as I mentioned, the observed alpha Mach number is a Borda unity, so it's actually not a very weak magnetic field. Okay, so they had several arguments. They had a number of arguments. I tried to boil them down. The first one is that the alpha of 2/3 requires spherical clouds, but the clouds in the Crutcher sample are not spherical. Well, this is just a completely false statement. The conclusion has nothing to do with the shape of the cloud. It has to do with the way the cloud contracts. So you have a cloud of arbitrary shape. If it undergoes a homologous contraction, then you'll get B going like rho to the 2/3. In fact, we looked at the aspect ratio of our clouds, and we found that they were generally between like 1/2 and 2 throughout the simulation. Now, we could not track individual clouds. We would take different snapshots, and because this is a turbulent medium, you can have clouds colliding with each other and merging and so forth. So I can't say that I have an isolated cloud and we followed it very carefully and it remains spherical. But when you take the different snapshots and you look at it, all the clouds are basically in this range, and that's consistent with approximately spherical collapse. The second argument is that they underestimated the uncertainties in the densities, and if you include the full range of observed densities, then lo and behold, you get alpha of 1/2. And in talking to Dick, he acknowledges that they just made a very rough estimate of the uncertainties, and it's quite possible, they said it's about a factor of 2, it's quite possible that the uncertainties are greater than that, but that there's no, at least he is not aware of any bias in those uncertainties. And my understanding from reading what Tritsis et al. Said is that they would take, look at the sources that Crutcher et al. Had, and then look in the literature and find a range, you know, what other people had said. And of course, other people might have looked at different resolution, and in particular for the CN sources, which are the densest ones, there are some observations which are at higher spatial resolution, and then you would get higher densities. But they would then use that as one of the densities that they would put in a very high value. Of course, there's no measurement of the strength of the magnetic field at that length scale, so they did not put in, presumably the field would be higher. They did not do that. So they then, at least in my view, systematically biased their slope so that the dense sources would be at higher densities, and that would flatten it out. The third claim that they made was that the distribution of field strength is described better by a log normal than a flat distribution. And what we found in our analysis was if you actually look at the line of sight fields, we tried 3 different distributions. We had a log normal, a flat distribution, or an exponential. And these are what you get. And basically, if you just look at these data, you can see that the projection effects spread it out over a factor of about 1,000 in the log of the line of sight field normalized by this density. And I can't really tell which of those is right. We were unable to determine from the line of sight field what the intrinsic distribution was. On the other hand, as I showed above, the simulated fields then are fit much better by a log normal than a flat distribution. So the conclusions then are the arguments that favoring alpha of 1/2, in my view, are without merit. Their claim that the alpha of 1/2 is, I point out, is also inconsistent with the direct observational result we found that if you just take for the observed line of sight fields, we get 0.63 plus minus 0.07. So that's inconsistent with 1/2. And the results of our simulation are consistent with their suggestion that the distribution of the simulated field strength is log normal, but we concluded that the sample size is too small to conclude this for the observed fields. So I'd now like to go to the final topic, which is try to look at the strength of the mean magnetic field, and we conclude that it's moderately strong with an Alfvén Mach number of order unity. So in fact, this Alfvén Mach number measures the strength of the field relative to the turbulence. So you have that it goes like rho b square root of rho b squared over b squared. And if I want to now evaluate this for the mean magnetic field, so this is the mean vector magnetic field. And if I have a strong mean field, that corresponds to having an Alfvén Mach number less than or of order unity. So that means that the uniform field is greater than or of order the random field. Whereas if there's a weak mean field, then this Alfvén Mach number is going to be much larger than 1. And as a result, the turbulence is going to make the field tangled. And Padouin and his collaborators have for a long time argued that, in fact, this is the correct description of the interstellar magnetic field. And I should say that when we undertook our simulations, it was my thought that because using an Alfvén Mach number of order unity and one much bigger than 1 unity, those are so different that we would just obviously be able to tell from our analysis of the clumps what the difference was. And but that, as you'll see, that turned out to not be true. In the observations, Huabai Li and company compared the Zeeman observations of clumps on very small scales using sub-millimeter observations of 0.1 to 0.3 parsec with polarization observations on GMCs on scales of 1 to 200 parsecs, often using the optical polarization. And the idea that those would be related was when I first saw that, I thought that was extremely surprising. And this then is what their results are. On this axis, they plotted the orientation of the field on very small scales, and on this axis, they have it on very large scales, the 1 to 200 parsec. And you can see there is, in fact, quite a dispersion, but what they found was that 90% of the cores have the magnetic field within 45 degrees of that in the ambient medium. So that means that the turbulence does not dominate the field. The Alfvén Mach number has to be less than or of order unity. And the cores may not be, may be magnetically supercritical, as has been argued before, and as I will argue again in my talk on Friday, but they can't be too supercritical unless the turbulence is very weak, because this relation between the mass to flux ratio, the virial parameter, and the Alfvén Mach number. So what did we do in our simulations? We did a strong field simulation, which I described to you a few minutes ago, which has the Alfvén Mach number of 1 based on the initial magnetic field. We also did a weak magnetic field one, where this Alfvén Mach number was 10. And then, as I said, we ran the simulation for 2 crossing times, and during that time, in the weak magnetic field case, the Alfvén Mach number dropped to 1.86 by more than a factor of 5 from the initial value. On the other hand, in the strong field case, the Alfvén Mach number only dropped by 15% because the field was already very strong. So the local properties of the weak field simulation were consistent with observation and with the strong field model. So in particular, we found that the magnetic field varied as density to the 0.57, and I didn't write in the error bar, but it was consistent with the 0.65 that was inferred from observation by Crutcher et al. And the means and medians of the line of sight field and the total field normalized to the density of the 0.65. They agreed within 25% of between the weak and strong field simulations, even though the initial field was 10 times weaker. So as I said, just looking at the local properties, we were unable to distinguish these 2 models, which surprised me. On the other hand, when we went ahead and repeated the computer with what Huabai Li did, then the strong field orientations are consistent with observations, and the weak field are random. So here we have the percent of the cases which are within 26 degrees or 45 degrees. This is the observed. And then in the strong field simulation, we have the 100 clumps. Then we also then looked at just the most massive of those clumps, the 25 most massive ones. And we find that, and I should say that the numbers outside are when you just integrate over the volume of the clump. If you then observers don't have that luxury. They look all through the line of sight. So this number is in parentheses if you look through the whole turbulent box. And you can see that these numbers are fairly close for the strong field simulation, both in this 26 degrees and the 45 degrees. On the other hand, in the weak field simulation are very close to a random orientation. So when it seems to me that this is very direct confirmation of the conclusion that Wabai Li and company reached, which is that the mean magnetic field in the interstellar medium is fairly strong. And so the conclusions for my talk are first of all, that the analysis of the line of sight fields and the simulations confirm the conclusions by Crutcher et al. That the magnetic field varies as a density to the alpha, and that alpha 0.65 is close to theoretically predicted value by Mistel, 2/3, for spherical contraction with the weak field. We were able to determine directly from their observations what the typical field strength is in these molecular clumps. And we confirmed their observational results by simulation, and we showed that this scaling here, this density scaling, is due to self-gravity. And we argued that the claim by Tritsis et al. That alpha, in fact, is 0.5 is invalid. And finally, we showed that the simulations by Wabai Li, that we confirmed their results in our simulation, that the mean magnetic field in GMCs is moderately strong. And in fact, the typical alpha and Mach number is of order unity. Thank you.
We have time for questions. Okay, Enrique.
Yeah, I quite very much agree that the fields should be on that order. That's what we find too. I'll mention that tomorrow. But I would like to point out that even in the very weak field case, you do expect alignment between the magnetic field and the velocity fields, because in that case, the velocity field is dragging the magnetic field along, and therefore, I'm not sure whether you could conclude that the field is moderately strong just by alignment, although I tend to agree with that. But so in one case, when the field is strong, the field drives the flow. And when the field is weak, the flow drives the field. But in both cases, there's alignment. In our paper in 2011, we showed that even in the weak field case, you tend to find more alignment.
I can imagine on local scales, you do get alignment. My point was that what we did was we compared the structure in our clumps, which are very small, compared with the average in the whole box. And we showed that in the strong field case, we got alignment consistent with observation. In the weak field case, the clumps are totally random. They are randomly oriented. They don't know what the average direction of the field is. So I think it's quite conclusive that the mean magnetic field does have to be reasonably strong in the ISM.
Hello, Chris. I agree with your conclusions. I guess the magnetic field matters, but I'm very curious why you didn't mention any of the Planck results, and you're referring to the lead. Do you have a particular reason for that? And the second part of the question is, did you look at the change in relative orientation in the less dense filaments or less dense structures in your simulation with respect to the highest density structures in the simulation?
No, we were focused. As I mentioned, we took out the 100 most massive clumps, and then we did, all our analysis was just based on that. So we were not trying, I think what you're suggesting to try to analyze the structure in between the clumps, which is what you get in Planck where you're looking at everything, would be very interesting, but that was not an issue that we addressed.
I have two questions. The first is, when we analyze the density magnetic field strength relation, do we need to worry about this coupling strengths between the neutral gas and magnetic field? And the second one is, what if the initial setting is magnetically subcritical for your simulations? Do you expect similar results?
Okay, so on the first question, these were ideal MHD simulations. And it's quite possible that on the smallest scales, bipolar diffusion might have an effect. In fact, we found that the fields inside the clumps are not that tangled, however. So we have tangling on the large scale, which would be unaffected by bipolar diffusion, but on the small scale, they're not that tangled, so I'm not sure exactly how much. I don't think there would be a big effect, but we, that we were unable to include that effect. And your second question was, which?
The second is what if the initial setting for the simulations
right,
is
whether it was subcritical. Yeah, so no, we have not done a subcritical. To have the whole box be subcritical, we have not done that. My anticipation is that nothing much would happen unless we were to drive it at extremely. If we drove it at a very high alpha Mach number, then we might be able to get some effects. But with an alpha Mach number less than a Borda unity, I don't anticipate that we would get any clumps or anything.
So, Chris, over here. Yeah, very nice talk. So one of the other conclusions from the Crutcher paper and subsequent papers looking at the difference between the massive flux in the core versus the envelope is that bipolar diffusion can't really explain the transition, and that reconnection diffusion is a possible mechanism that can. So are any plans to test what's causing the change in the massive flux, and then other results here that have confirmed the Crutcher results in the simulations?
Well, I didn't, as you noticed, I didn't talk about mass flux in this paper. I'll talk about it on Friday. But we, again, we analyzed the total mass to flux ratio. I'm not sure, we felt, and we did a resolution study to verify that our results for the total were converged, to try to then go in and study the structure of the field in the clouds. We would be perhaps pushing our resolution. We might need to go to higher resolution. And of course, if we wanted to look at the effects of bipolar diffusion, we'd have to include that. We did some work some time ago on bipolar diffusion, and as you probably know, it's a very challenging problem numerically, because if you have a diffusion problem, the time step tends to go like the square of the size of your cell, and so high resolution simulations become very difficult. We introduced an approximation, but that approximation nonetheless takes 10 times longer than a normal simulation. So,
but these simulations should have reconnection taking place because there's turbulence. So
yeah, and so I'll mention that we have some evidence for either reconnection diffusion in these simulations. I'll mention on Friday.
Last question, Eric.
So, Chris, what can you say about the evolution of the turbulent kinetic and magnetic energies? I mean, one might suppose that these would react on each other and evolve toward equipartition at some time. What did you find in your simulation?
Yeah, so first of all, I should point out that these were driven simulations, so that we forced the total Mach number to the sonic Mach number to remain constant during the simulation. And then, as I said, during the first phase of the simulation where we did not have self-gravity, the alpha Mach number decreased slightly. There was some tangling of the fields in the strong field case, and then it stayed about constant. Whereas with the weak field, it then built up to, the alpha Mach number dropped by a factor of 5, approaching equipartition. And in terms of self-gravity, the clumps were continuing to collapse. In this simulation, we did not introduce sync particles. Since then, we have continued the simulation with sync particles, and we are forming stars. So the gravitational energy will continue to increase.
Let's thank Chris once again.